In these alligator-infested backwoods, the final piece in the puzzle of Einstein's universe is being put to the test. This place stands at the leading edge of the exploration of gravity.
Really what we want to do here.
Joe Giami is the head man.
Gravity will probably and hopefully confuse us for a long time before we figure out what it really is. And scientists are happy when they're confused and hot on the trail of something fun.
This is the Laser Interferometer Gravitational Wave Observatory, or LIGO for short.
Any signal we see is going to be from something really, really interesting and cool. Data from those kinds of sources would be really valuable to learn things about gravity and the nature of gravity.
This machine was built as an observatory, a chance to witness violent galactic events beyond anything we've ever seen before. One of the things I hope to see is when you get two stars called neutron stars. Now, a neutron star is probably twice or three times as heavy as the sun, but compressed into a ball about 10 kilometers across, so the size of a city. And there are places where there can be two of those things orbiting around each other at about 100 or even 1,000 times a second. The incredibly dense neutron stars spin round each other, churning up the space-time. As they spiral in, going faster and faster, Einstein predicts this sort of violent cosmic event will create something called gravitational waves. But what exactly is a gravitational wave? It's not that easy to describe. If a wave came through this room, it'd... what did I say? Ripples, yeah. Space-time isn't just something that's, you know, up there amongst the stars. It's here, right? It's in front of me and it's inside me. So when I move, I disturb it. I send out ripples in it. It's just like if I jump into a swimming pool and start swimming, I'll send out ripples on the surface of the water. It's the same with space-time. In theory, these waves would cause space and time to stretch and shrink as they pass through the universe. These waves are physical distortions in our reality. You know, they really are stretching and contracting the space and the time that we're in. But trying to see these gravitational waves using the LIGO machine is proving very difficult.
Gravity waves cause lengths to change in one direction differently than the other direction. So if I were very stretchy and a gravitational wave were going through me, this is what would happen. I would get shorter one way and longer the other way.
The machine works by using a laser beam to measure the distance between two sets of mirrors suspended at the ends of the two 4-kilometer-long tubes.
So from up here you can see pretty much all the key components. You can see running off to the right there and also running down under our feet are tubes that carry the light to the end stations. So there's a mirror here and there's a mirror 4 kilometers over that way. And when the gravity wave comes through, the distance between those mirrors changes.
They're basically just fancy rulers.
That's right, that's right.
But even after 5 years in continuous operation, the team hasn't been able to observe any violent gravitational hotspots. This is because they still haven't detected Einstein's elusive gravitational waves.
This is one piece of nature we haven't really observed right yet, to see gravitational waves, whether they really affect things here the way we think they do. We don't know where the sources are that we're looking for, so we have to look farther and farther out until we catch one.
If we can figure out how gravity works at the level of the smallest subatomic particles, then maybe we can finish what Newton and Einstein started and form a complete picture of this mysterious force of gravity. To achieve this goal, we have to try to recreate the conditions of the Big Bang here on Earth. and peer deep into the heart of the subatomic world. This place is Fermilab, and I used to work here. It's home to the Tevatron particle accelerator. The Tevatron basically works by bashing stuff together and seeing what comes out. What we do is we take protons, we accelerate them around that way, and antimatter protons, send them around that way, and they pass by here 50,000 times a second, very close to the speed of light. And then we collide them together, we smash them together. It's through collisions like these that the nature of matter has been revealed. But the force of gravity still sits outside what we know. One of the ways we might get to the truth about gravity is to try and fit it into the beautiful framework we have that describes the subatomic world. Quantum mechanics predicts that the force of gravity should be transmitted by a particle. We've called this particle the graviton. If we could just find these gravitons, then we might at last arrive at a quantum theory of gravity, a universal theory that will work everywhere in the cosmos. For 8 years, Greg Landsberg has been using Fermilab's particle accelerator to try to create gravitons.
These particles, well, we haven't quite seen them, so what I'm telling you is we
Haven't
just
quite seen them.
That's right. It's our hypothesis, so we don't quite know if this is true or not. It's not that we can shine light on gravitons to see them, so we have to find some other means. It's amazing that the way to see the graviton is by not observing it, by observing its missing.
To see something that's missing, Greg is effectively looking for missing energy. Typically, when you bash things together, the energy of the original particles should be the same as the total energy of all the particles coming out. But if you were to make a graviton in that collision, then our detectors are certainly not capable of seeing it. So the graviton will take energy away from the collision. Energy will appear to disappear. So the old D0 control room, I've been here for years.
So what this picture tells us, it's called event display. The height of these bars is how much energy is released in this collision in that particular direction.
So you've got a collision in the middle there, and
Right.
there's stuff spraying out.
And so what we're trying to do is to sum all this energy to see if something is missing. If you look at this display, you see a lot of energy going in this direction, but very little on the other side. And this yellow bar, in fact, represents the fraction of energy which is missing.
All right, so if you see that, that means there's something escaped.
That's right.
If gravitons are created, Greg believes the reason why they would disappear is because they vanish into a place beyond our reality, into some sort of extra dimension. Now, we're all familiar with the 3 dimensions of our world. As up and down and north and south and east and west. But what scientists like Greg are proposing is that there can be extra, hidden, unseen dimensions. It sounds ridiculous, and it is impossible to picture, but theoretically it's possible. And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions.
If gravitons really are created and they escape in these extra dimensions, we would never see them. Although it might sound like a very odd hypothesis, an odd concept, really nothing prevents us of thinking in this direction, especially if we can solve these mysteries.
Newton could predict the effects of gravity. Einstein worked out why it exists. But by finding a graviton, we might at last truly understand gravity.